Hi and welcome to this latest video on support vector machines. Now what I'm going to talk about today is the kernel trick. This is one of the most important aspects of support vector machines and how to use them in practice. It's also quite involved, and if you haven't seen the second video on SVMs that I've done, the one on Lagrangians, I'd suggest you look at that one first, because that really gives you the basics for how you move from the standard method of looking at support vector machines to the kernel trick, which is, as I say, it's really important. It's whenever you start looking at SVMs in Python or in R, they'll give you the choice of what kernel to use. And whilst it is possible to play around with these kernels and play around with the parameters without knowing what the kernel actually does or what it represents, I think it's better when you're looking at something like SVMs to really understand exactly what you're doing, exactly what's going on. So I'm going to try to do that over the course of the next few videos, because it is quite heavy going in parts, but hopefully you'll find it rewarding. So let's start by just recapping what we're trying to do with an SVM, a support vector machine, in the first place. And let's start with the easiest version, which is a hard margin where you've got two different measures that you're looking at. So the hard margin is defined as beta1 x1m plus beta2 x2m minus beta 0 equals 1. And anything above this line has to be something where ym equals 1. And beta1 x1m plus beta2 x2m minus beta 0 equals minus 1. So anything below that has ym is equal to minus 1. So ym equal to 1 means it's, say, a solvent firm. Ym equals minus 1 is an insolvent firm. And those are the margins of the best separating line, the lower and upper margins. And the width of the margin under that formulation is 2 over root beta 1 squared plus beta 2 squared, which is equivalent to 2 over the norm of the vector beta, as we'll see later on. At any point sitting on these margins are known as support vectors, and they also become quite important when we're looking at the kernel trick and when we're looking at Lagrangians. So, two key features about this margin. The margin width is 2 over root beta 1 squared plus beta 2 squared, which implies that the margin rises as beta 1 squared plus beta 2 squared falls. And you want to have a margin which is as big as possible. Also, the margin constraints imply that ym times beta 1 x1m plus beta 2 x2m minus beta 0 has to be greater than or equal to 1 for all x1m, x2m, ym. And if you remember, that is the set of points for firm M, which describes the measure x1, the measure x2, and ym, whether it's solvent or insolvent. So if we're trying to make the margin as wide as possible, but still making sure it's a hard margin, so everything is either on one side of the margin or the other, so it's either greater than the upper margin or lower than the lower margin, we need to minimize beta 1 squared plus beta 2 squared, subject to ym times beta 1 x1m plus beta 2 x2m minus beta 0 is greater than or equal to 1. Now, if we generalize this for k variables, as you remember, then instead of just x1m and x2m, we go all the way out to xkm, and we call that the vector xm, which is in bold. And then we're redefining the set of points as bold xm, so the vector xm comma ym, where m is equal to 1 to m for m firms. And the separating plane or hyperplane becomes beta 0 equals vector beta transpose xm, where this vector beta is beta 1, beta 2, all the way up to beta k. The margin becomes beta transpose xm minus beta 0 equals 1 to beta transpose xm minus beta 0 equals minus 1. So we're just doing this in a higher number of dimensions. And the width now is explicitly 2 over the norm of that vector beta, which is 2 over the square root of beta 1 squared plus beta 2 squared all the way up to beta k squared. So the problem now is minimizing the norm of beta squared, or the norm of beta, it gives you the same result, subject to ym times beta transpose xm minus beta naught being greater than or equal to 1. So this is just the k variable version of what we're looking at, and most of what we'll do will be in vector space. Now, we saw that moving from 2 to 3 dimensions allows the data to be separated by a plane, and we could even move to higher dimensions. So what we were looking at was adding a squared term when we were looking at that quadratic, which was the best separating line with one extra dimension. But you could have a 5-dimensional form if you wanted. So beta naught is equal to beta 1x1m plus beta 2x2m plus beta 3x1m x2m, beta 4x1m squared, beta 5x2m squared, and so on. So if you do this, it does give you a slightly better fit with very small weights on the new parameters. So if we look here, you can see in cells K2 and M2, that's the 2 new variables compared to the stuff that we did in the last video. And beta 3 and beta 5 are very small. So it improves the fit a little bit, but not an awful lot in this case. But when you're doing it, what you find is that convergence does take longer because it's computationally more intense. You've also got this thing called the curse of dimensionality, which essentially, if you think about a finite number of points and how they would look on a 2-dimensional grid, and if you look in the bottom corner, you'd have a small number of points. Well, if you went from a 2-dimensional grid to a 3-dimensional cube, and you look in the bottommost cube, well, the number of cubes that there are is an order of magnitude greater than the number of squares there were in 2 dimensions. So the number of points in each of those little cubes also drops by an order of magnitude each time you increase the number of dimensions. So it gets less and less robust to fit things as you increase the number of dimensions for the same number of data points. It's something you see a lot when you're dealing with copulars as well, which hopefully a lot of you will be familiar with in the other series of videos that I've done. So the solution to this is to use a kernel, and I'm going to use a lot of terms here which will become more clear as we look at examples of them. But what a kernel does, it avoids you having to explicitly map from what's known as input space, so the data they're actually looking at, to feature space, which is some function of that data. And what it does instead is it represents the objects in terms of pairwise relationships. So what this really means is, instead of having these complicated functions with lots of cross products and so on, you're just looking at the dot products of pairs of coordinates. And this can be done by adapting the Lagrangian approach, which is why it's very important to understand what's happening with the Lagrangian approach to SVM. And the reason for this is that the Lagrangian approach actually uses dot products in its formulation, so it does most of the work for us. So just going back to the Lagrangian, if you remember that when we're looking at the hard margin SVM, what we're trying to do is minimize the norm of beta squared over 2. Now that's the same as minimizing the norm of beta squared, but when you go to the soft margin, the over 2 becomes quite important in that formulation. So that's why I've got it back here. So we're trying to minimize the norm of beta squared over 2, subject to ym times beta transpose xm minus beta naught being greater than or equal to 1. So the Lagrangian formulation changes this, and it changes it to try to maximize the sum over all m of Cm, that's the Lagrangian multiplier, minus the sum over all m and all n of Cm Cn, Ym Yn, Xm transpose Xn over 2 with respect to Cm. So the kernel trick starts with mapping from the input space Xm to the feature space of phi of Xm for firm m. And this will become clearer when we start looking at examples. So here is a simple example. Say you've got 2 accounting measures for a firm m, x1m and x2m. So it could be, say, EBIT over assets could be x1 and log of assets over liabilities could be x2. We could have a mapping of this, of xm, which would be phi xm, and this would be phi xm is equal to phi of x1m, x2m transpose. So the kernel method avoids having to do this explicit mapping through the use of a kernel matrix. So what's a kernel matrix? So here on the right we've got the kernel matrix, and it is basically a kernel of each of the pairs of variables, or rather each of the pairs of firms. So we've got m firms here. We're looking at the relationship between firm 1 and itself in the top left corner, then firm 1 and firm 2, all the way to firm 1 and firm m. And the kernel function is defined as k xmxn is equal to phi xm transpose phi xn. So essentially the dot product between phi of xm and phi of xn, those transformed versions of xm and xn. Now what this means is that instead of transforming from the input to the feature space explicitly, if you build this kernel matrix which represents the relationships between these pairs of firms, the values for these pairs of firms, then the kernel represents the dot product in feature space. And the neat thing about it, as we'll see, is that you can calculate it without directly constructing phi of xm. Now this means that there is a finite number of kernels that exist. There has to be something where, even though you don't refer directly to the input space, it's something that you could convert it to input space if you wanted to, for it to be an explicit kernel. So this is the simplest kernel of all. It's the kernel where phi of xm is just equal to xm. So it's equal to x1m, x2m transpose, so it's equal to that vector. So we know that k of xn is equal to phi of xm transpose phi of xn. And you can expand this to give k xn is equal to x1m times x1n plus x2m times x2n. So that's essentially the dot product of those two vectors. The x1 for m and n multiplied, x2 for m and n multiplied, which gives you x1m, x1n plus x2m, x2n. But we also know that x1m, x1n plus x2m, x2n is just equal to xm transpose xn. That is equal to the dot product of those two vectors. So in this case, k xm xn is just equal to xm xn. Now this is a trivial example, I know, but it's just showing you what we're doing. So when we move on to something a little bit more complex, you'll see the methodology that we use to get there. And also we can show what this means with a numerical example. So say we've got x1 equal to 0.18 and 0.31, and x2 equal to minus 0.11 and 0.17 for firms m and n respectively. What this means is that k xmxn is equal to 0.18 times 0.31 plus minus 0.11 times 0.17 equal to 0.371. So this is straightforward. But this is less straightforward, and you can see why it becomes useful when we start looking at a more complex kernel. So let's have a more complex kernel. This is the quadratic kernel. Now the transform here is a bit more complex. What we've got here is a transform where phi of xm is equal to x1m squared, x2m squared, root 2 x1m, x2m, all transposed. So if you remember, xm is simply x1m, x2m. It's a vector with two elements. Here we've transformed it into a vector with three elements, and we're squaring each of the elements and then looking at the cross product. And then we've got this strange root 2 in there, which for reasons which will become clear. So as before, k xmxn is equal to phi of xm transpose phi of xn. And as before, we can expand this to give k of xmxn being equal to x1m squared times x1n squared plus x2m squared times x2n squared plus root 2 x1m x2m times root 2 x1n x2n. So essentially we're looking at the dot product of those two vectors, which means that each of those elements gets multiplied by the corresponding element in the other vector, the vector for m and the vector for n. And this is equal to x1m squared x1n squared plus x2m squared x2n squared plus 2 x1m x1n x2m x2n. So far so good. However, we also know that that long expression is actually equal to x1m x1n plus x2m x2n all squared, or the vector xm transpose xn all squared. So that kernel kxm xn is actually equal to xm transpose xn all squared. Now this is important because it shows that you can evaluate the kernel directly from the input data without having to do that phi mapping first. So we can verify this numerically. So again, x1 is equal to 0.18 and 0.31, x2 minus 0.11 and 0.17 for firms n respectively, as before. And this is what the phi xm and phi xn give you. 0.18 squared minus 0.11 squared, root 2 times 0.18 and minus 0.11, 0.31 squared, 0.17 squared, and root 2 times 0.31 times 0.17. So k xm xn, you take each of those elements and multiply from a vector m, vector phi of xm, and you multiply it by the corresponding element in vector phi of xn. So you get 0.18 squared times 0.31 squared plus minus 0.11 squared times 0.17 squared plus 2 times 0.18 times 0.31 times minus 0.11 times 0.17, you get 0.00138. Fine. Now, that's doing everything through that transform of the vectors. However, k xm xn is equal to xm transpose xn all squared. So you can also calculate it as 0.18 times 0.31 plus minus 0.11 times 0.17, and then square the whole lot, and you still get 0.00138. In other words, you get exactly the same result, but you haven't had to do any of that mapping. And that's why the kernel method is so important. You don't need to do the complex mapping. You can bypass that to just look at a much simpler function of the initial data, the underlying data. Now, remember, our goal with SVM is to try to maximize 2 over root beta squared. We're trying to maximize the size of that margin that we've got. And this is equivalent to minimizing root beta squared over 2, subject to ym times beta transpose xm minus beta naught being greater than or equal to 1. And remember, the Lagrangian approach frames this in a single function as L equals the norm of beta squared over 2 minus the sum of Cm times that function, where and so what you're actually doing is you're multiplying the constraints by those Lagrangian multipliers, C1 all the way up to Cm, where Cm is greater than or equal to 0. Do a bit of calculus and you find that the norm of beta squared over 2 minus that summation is actually equal to the sum over all Cm's, the sum over all m's of Cm minus the sum over all m's and n's of Cm Cn, Ym Yn, xm transpose xn over 2, and you need to maximize that with respect to Cm, subject to the sum of all the Cm Yms being equal to 0 and Cm's being greater than or equal to 0, or if you've got a soft margin, Cm being between 0 and 2m lambda to the minus 1. And if any of that's unclear, if you go back to the second video, cover that in more detail. So, if you want to use the kernel trick, you want to use some transformed version of xm, in other words, phi of xm. And all you do for a Lagrangian is you just substitute that directly into the Lagrangian. So you end up with the sum over m's of Cm minus this double summation of CM YM phi of xm transpose phi of xn over 2. But we know that phi of xm transpose phi of xn is equal to k xm xn, in which case you can just stick that straight into the Lagrangian as well. In other words, what you need to maximize is this function here, which doesn't refer to that transform data at all. It just refers to the kernel that you are using, which means you can avoid having to carry out the mapping into feature space. And the values of CM can be found from the optimization as before. And when you've done that, you can then just take that information and stick it back into the original formulation, or into this formulation here, to work out what the values are for vector beta, because the values of vector beta are just the sum over m of CM YM phi of xm, so that's the only time you ever need to use that transform, and beta naught is equal to beta transpose phi of xm minus ym. Okay, so you need to use phi of xm twice, but only when you're back solving for the betas, not in the optimization itself. So here's an example using the quadratic kernel. Now we know the quadratic kernel is k of xn is equal to xm transpose xn all squared. So what that means is we need to maximize the sum over all m of cm minus the sum over m and n of cm cn ym xm transpose xn all squared over 2. So we can ignore the transform that got us to this kernel in the first place. So here's an example of the quadratic kernel trick. Now, as we said before, that kernel, if you expand out xm transpose xn all squared, you get this formula here, which is the formula for an ellipse, which implies that this kernel works best on data which is either close to or far from a central point, which is not ideal for credit modelling. We'll cover a more appropriate kernel for credit modelling later on, but it's a useful example because it's just complex enough not to be trivial, but it's not so complex that you get lost in the fact that the mapping is actually a little bit more involved, as it will be for some of the other kernels. So it's a useful way to learn what's happening with the kernel trick. So this is the basic SVM approach. And what I've done here is I've started with a soft margin SVM and then moved to a hard margin SVM to find my betas. So here, the soft margin SVM, this formula should be familiar from one of the earlier videos where we look at how to calculate a soft margin SVM, and you'll see it gives you some betas there. So beta naught about minus 3.9 minus 4, beta 1 minus 108, beta 2 minus 88, beta 3 minus 51. And we're performing that on EBIT over assets squared, log of assets over liabilities squared, and root 2 times EBIT over assets, log of assets over liabilities. So we're doing it based on that transform, but just on the raw data. And you do the reason I do it, try and find the soft margin SVM first, is because just computationally it's a little bit easier. And it gives us some starting points for our betas for the hard margin SVM. And I know with this data that you can find a hard margin. So I take the betas from F2 to I2, plonk them into M2 to P2, and then I use those to find the hard margin SVM, which you'll see isn't hugely changed, but it's a little bit better. I mean, you can see the norm of beta squared has dropped from 22,000 to about 20,500, so it's a little bit better. But anyway, that gives us some answers for beta: minus 3.8, minus 104, minus 84, and about minus 50. So that's the old-fashioned way. You can also do it the Lagrangian way. So the way you do this, if you remember, is you multiply the C's in here L7 and P3 by the Y's in M7 and P4, then by these matrix multiplied offsets, where we're multiplying essentially the values in columns B to D for each pair of firms. And that gives us a fairly large matrix of those values, which we then sum. And we combine that sum with the sum of the C's, because that's essentially what happens when we're trying to calculate what we are maximizing for the Lagrangian. And you'll see the maximum value we have in L1 is 9,817, which is made up of that sum of the CMs minus a half of the sum of that that large array of the C's and the Y's and the 5x transposed. And you'll see the results that we have there for beta 1, beta 2 and beta 3 are pretty close to the numbers that we had using the traditional approach. And again, the beta naught, which is calculated from the support vectors in column F, again pretty close to the ones that we did the old-fashioned way. And as you can see, the way that we found these betas is looking at the sum product of all of, in this case, column B and CY to give us beta 1, beta 2 just looks at column C instead, beta 3 column D, and the beta 0 is derived from the values of ym, the values of the vector beta, and the values of EBIT over assets squared, log of assets over liabilities squared, and roots 2 times EBIT over assets times log of assets over liabilities for the support vectors. And if you recall under the Lagrangian approach, the support vectors are the only ones which actually have a positive value of C. Everything else, the value of C is 0. So that's what the Lagrangian SVM approach looks like, where you're looking at using the transformed data, EBIT over assets squared, log of assets over liability squared, and roots 2 EBIT over assets times log of assets over liabilities. What about if we move to the kernel trick approach? Well, the first thing to note is that the maximised value is almost identical. So look at J1, you've got 9,817.77, very close to the value in L1 of 9,817.7763. So you're getting the same value even though you're using a different formulation, using the kernel. And we can see the way that works by looking at this formula here, because again you've got the two C's multiplied, the two Y's multiplied, but then what we're looking at is multiplying the indirect of those two locating formulae, and that is just EBIT over assets and log of assets over liabilities multiplied for each pair of firms, but the result then squared. So that's using the kernel trick, the fact that the kernel is xm transpose xn all squared, rather than using the transformed data, which is really quite interesting. And again, we sum those, we sum the values of C, and that gives us, as before, this formula of the sum values of C less that summation over all the firms, and also just the sum of all of those values of CY is equal to 0. That's just one of the constraints that we had. But that gets you to essentially the same result in terms of the values of C. So if you compare those values of C to the ones that we had using the Lagrangian, they are the same, which is really interesting. Now, as noted before, the transformed data is in the form of an ellipse, and this is the best separating ellipse for that data. And it shows you that you can do it through either the traditional approach, you can do it through the Lagrangian approach, or you can do it through the kernel trick approach. Now, I would say that doing it through the kernel trick approach and the Lagrangian approach, whilst in theory it should be straightforward, I mean, in practice doing that through Excel, it took a lot of iterating to actually get to the support vectors. So it wasn't as straightforward as it would be if you're using something like R, which seems to calculate these results almost instantaneously. But it is something which can be done in Excel, and as I often say, if you do something in Excel, it does help you understand exactly what is going on, what's underneath the data. So that's the introduction to the kernel trick and how it works and what it's doing. I'd advise you to spend some time just going over this a few times to make sure you understand what's going on, because it can take a bit of effort to understand what we're trying to do with the kernel trick and why the different stages work, why they do what they do. But I do think it's worth it, so that when you're using SVMs in something like R or Python, you understand the rationale for what's going on and why it works. When we come back, what we'll talk about is a few more kernels and how they work, and look at some more useful kernels for credit modeling. And then after that, I'll show you how to do it in R and show you how simple it is there. But hopefully you'll recognize that whilst it is simple in R, it's actually quite helpful to know what you're doing, to understand the rationale for something which looks very straightforward in a program like R. So until next time, I hope you enjoyed this video, and I shall see you soon.